In this video, we study Bernoulli Rule type 2. Type 2 means you get products like 0 times infinity. It can be one of those infinities. So you have one function which goes to 0, the other function which goes to infinity, and then we get 0 times infinity. So this is another indeterminate form, because you can see that when you have 0 times infinity, we really don't know what can happen. It can be 0, it can be infinity, or it can be a number. And also the Bernoulli rule, sometimes we also call the L'Hopital's rule, which is a historical mistake because this rule was introduced by Bernoulli. So we're going to call this Bernoulli rule instead of L'Hopital's rule. So let's talk about the theory part. Um, so we use when we have indeterminate form, use for indeterminate form. Use for indeterminate form 0 times infinity. So that means when you try to find the limit when x goes to 0, not 0, like some a, fx times gx. So you have two functions. So what will happen? This is going to go to 0 times infinity. So that's the case we are looking for. It's going to be 0 times infinity. And then, so this is the method. So what we're going to do, so the first step, you're going to bring it to, so we're going to say bring it to either 0 over 0 format or infinity over infinity format. Form by dividing. So it will be very clear, like when you look at an example, what we mean by that. So we can divide by the mostly the easier one. And then after we do that, then we can use type 1. So we can use a type 1 Bernoulli to get the answer. So let's look at a problem and see how it's gonna go. As the first problem, we have limit when x goes to 0 plus x times ln x. So if you look at the graph of natural log function, and you can see that the graph looks like that. So that means when x goes to 0 from right, you can see that the ln goes to negative infinity. So that means this problem is a 0 times infinity problem. 0 times infinity problem. That means we exactly don't know what's going to happen. So according to theory, so first we can write this one as is a 0 times infinity problem. So what we can do, we always write it right like above the equal to sign to kind of the condition what we're trying to do here. So what we're going to do, you can see that we have a polynomial like x term and a other function like natural log function. So you can see that the x is like easy to manipulate. So what we can do, we can divide the top and the bottom by x. So then if you divide the top and bottom by x, what will happen? This is going to be ln x divided by 1 of x, because you divide the top and bottom by x. Right after we do that, you can see now when x goes to 0 plus, the top goes to infinity, negative infinity, and the bottom also goes to infinity, because you remember the graph of 1 of x. The graph of 1 of x is like this. So it's going to go like that and then like that. So that's the graph of 1 of x. So this is a graph of 1 of x. This is a graph of ln x. So you can see when x goes to 0, the function goes to infinity. So that's the case. So now what we're going to do, according to the Bernoulli rule, we're going to consider the derivatives now. So we're going to consider derivatives. So derivative of ln x, that's also we know derivative of ln x is 1 of x. So it is 1 of x divided by how to find the derivative of 1 of x. So what we normally do, we can write 1 of x as x to the negative 1 and then use a power rule. So if you the power rule, derivative is negative x negative 2 and then this is negative 1 of x squared. So that's the derivative. That means the bottom is negative 1 over x squared. Now we need to simplify this one. To simplify, what we can do, we're going to multiply the top and bottom by x squared. We multiply by x squared. So when you multiply by x squared, you can see, so you can pull the negative sign out. So you can see what you're going to get is limit x goes to 0 plus. You can see in the numerator, you get x. In the denominator, you get 1. So we can write it like that. We don't write 1. So that means when x goes to 0, 0 plus, this one goes to 0, that means it is 0. So the answer is 0. So this is like a very interesting result. So when x goes to 0 plus, x ln x goes to 0. So let's look at the next one. As the next one, we have x goes to infinity, x squared e to the negative x. So this is also very interesting. So let's again recall the graph of these functions. We know how x squared, but what is the graph of e to the negative x? E to the negative x is the decaying function, so it's going to go like that. So it passed through 1. So that's the graph of e to the negative x. So that means when x goes to infinity, you can see the first function goes to infinity, the second function goes to 0. So it's again a 0 times infinity problem. So what we're going to do is, again, we're going to bring this to either infinity over infinity or 0 over 0 times. So in this case, actually what you can do is you can bring e to the x to the denominator. So we can write it like this. So limit when x goes to infinity, I'm going to leave x squared here and bring e to the x down. Change it because it's a negative index, so it's going to be positive index. Now what we can do, and you can see after we do that, this is going to be infinity over infinity problem. So we can use the Bernoulli rule here. So that means we can take the derivative. So you can see x goes to infinity, take the derivative which is 2x, take the derivative which is ex. And once you do that, you can see the power reduce, but still you can see it is of the infinity or infinity type. So that means we can use the Bernoulli again. So that means the limit x goes to infinity, x goes to infinity is 2 over ex. Now at this step you can see that there are no x anymore. So and then clearly when x goes to infinity, we know that the ex goes to infinity. So this is a graph of ex function. And when x goes to infinity, ex goes to infinity. So that means a constant divided by infinity. That means is the fraction going to be smaller and smaller. So that means this is going to go to 0. So the answer is 0 in this case. This is also very useful in the future. So if you are taking like integration by parts, if you are learning integration by parts or series, so you're going to use this result. So it's a good thing to remember. So x squared e to the negative x goes to 0. So let's look at the next example. As the next example, we have limit x goes to infinity, x sine 1 over x. So when x goes to infinity, we know that sine 1 over, actually 1 over x goes to 0. So this is sine 0. And if you look at the graph of sine, and you know that, so this is the graph of sine, so it's going to go like that and go through 0. So that's the graph of sine. So if you look at the graph of sine, and you can clearly see that, so this is sine x, at 0, it's going to go to 0. So that means the sine 1 of x goes to 0 when x goes to infinity. And then x goes to infinity, so it's again an infinity times 0 problem. So as before, what we're going to do, we're going to bring the easier term to the denominator. In this case, the easier term is x. So what we're going to do, we're going to leave the x term, we can leave the sine 1 of x in the numerator and divide the top and bottom by x. When you divide the top and bottom by x get cancelled in the numerator, is going to go 1 of x. So that's what happened. So normally like this kind of problem you can actually solve using a different trick. So what we normally do is, hopefully you remember, we can let h equal 1 of x. And then once you do that, and you can see that when x goes to infinity, you can see h goes to 0. And then we can use the limit h goes to 0 sine h over h equal 1 result. This is also like you can prove using the Bernoulli rule. So this is like one of the results that you want to remember. When h equals to 0, the limit is 1. But now we can see how we can use the Bernoulli rule directly for this problem. So and then you can see when in this case as before, so when x goes to infinity, 1 over x goes to 0. So because of that, and then also sine 0 is 0. So we know that is a sine 0 is 0. So because of that, this one going to 0 over 0. So what we can do as before, take the derivative. So let's take limit when x goes to infinity. So let's take the derivative. So how to take the derivative? You have to use the chain rule for this problem. So if you are not familiar with the chain rule, you can look at the link in the description to learn about more about chain rule. So sine become cosine 1 over x, no change, and then multiply by the derivative of 1 over x. In the previous problem we did the same thing. So we can write 1 over x as x to the negative 1. So you can write 1 over x as x to the negative 1 and then use the power rule. So if you do that, you can see you're going to get negative 1 over x squared. That's what you get. And the same thing in the denominator, negative 1 over x squared. Now you can see this term is the same, so you can cancel out because this term is outside. So cancel out. So you simply get limit when x goes to infinity cosine 1 over x. Now you can see when x goes to 0, 1 over x goes to when x goes to infinity, 1 over x goes to 0. But now from the cosine graph, we know this result. We know that cosine 0 equals 0 from the cosine graph. So because of that, actually not cosine 0 is 0, cosine 0 is 1. So cosine 0 is 1 from the cosine graph. So, and because of that, this result answer is 1 for this problem. So you get 1 for this one. So as the next one, we have this interesting problem. Limit when x goes to 1 plus ln x times tan pi x over 2. So let's see what happened here. And we know the ln graph, but we also know what is the graph of tan. So you can see graph of tan has two vertical asymptotes. Actually, there are infinite many asymptotes, but for our case, we need this one. So you can see it's gonna go like that, and the pattern gonna repeat. So that's the shape of the tan graph. This pattern gonna repeat. That's the graph of tan. And this is 0. This is pi over 2. So when x goes to 1, what we have is tan pi over 2, but it's going from the larger values. So that means you can see the graph can go to a negative infinity. So it's going to go to negative infinity. So this is the infinity part, and then you can see when x goes to 1, natural log. So if you remember the graph of natural log, so it is like that. So you can see when x goes to 1, so ln x goes to 0, but it's go to 0. So 0 times infinity. So now what we can do for this one? So what we can do is, the easiest thing that we can do is move the tan function to the denominator, because we know that the 1 over tan is cotangent. So because of that, you can write this one as limit when x goes to 1 plus ln x. So we're going to bring the tan term to the denominator. So it's going to be cotangent pi x over 2, because cotangent is 1 over tangent. Now what we can do, and then you can see right after we do that, when x goes to 1, this is going to be 0 over what will happen to cotangent? We know that tangent pi over 2 going to infinity. So cotangent is 1 over tangent. That means cotangent goes to 0 at pi over 2. So this is 0 over 0. That means you can use the Bernoulli right now. So what we do, we take the derivatives, so as before. So as the ln x, that means 1 over x is the derivative. And the cotangent, derivative of cotangent is the negative cosecant squared. So we're going to get the negative cosecant squared pi over 2 times x times the derivative of the inside function, which is pi over 2. That's from the chain rule. Now see what's going to happen, and you can clearly see that when now you can actually plug in x equal 1 here. Or if you want, you can actually bring this term to the numerator. So you can switch the terms because they are in the 1 over. So we can write, this is like not a necessary step, but if you want to make it clear, you can do that. So I'm going to bring the negative sign in front. That's one thing I do. And then cosecant squared, we know that the cosecant is 1 over sine. So we can write this one as sine squared pi x over 2. And the 1 over x, if you divide that, if you multiply the top and bottom by x, x is going to go down. And then we have this one also, you can write this one 2 over pi. Pi over 2 becomes 2 over pi because it's in the denominator. Now, let's see what will happen when x goes to 1. When x goes to 1, you can see that sine term with sine pi over 2 is 1. So this whole term goes to 1. And the bottom is also goes to 1. So you're simply getting 2 over pi. So the answer is 2 over pi. So that's how you can do this problem. So let's do one more problem before we finish this. So this is the extension of the example number 1. So let's have this result. As the last problem of this type, we have the following one. So we have limit when x goes to 0 from right, x to the p ln x. So where p is positive, so let's assume that p is positive, because otherwise we cannot do this problem because we don't know what's the behavior of the function. So and then you can see that when x goes to 0, since p is a constant, x to the p goes to 0, and then ln x goes to negative infinity, so it's infinity, because you can remember the graph of ln x looks like that. So and then you can see that when x goes to 0, so you can see ln x goes to negative infinity. So it's a large number. And then x to the p goes to 0 because p is a constant. So that means this problem is simply a 0 times infinity problem. 0 times infinity problem. So what we're going to do is from the theory, we need to bring one of the terms to the denominator and bring it to type 1. So you can see that the easiest thing that we can do is, so limit x goes to 0 plus, the easiest thing that we can do is divide the top and bottom by x to the 1 over x to the p. So 1 over x to the p. So divide the top and bottom. When you divide the top, it can cancel out. When you divide the bottom, you get 1 over x to the p. Okay, so now right after we do that, and you can see this problem is now, because ln goes to infinity, so it's infinity, and then x to the p goes to 0, that means 1 over goes to infinity, because you try to divide by a very small number. So that's what happened. So now what we do, according to type 1 theory, we want to find the derivative of the top and the bottom. So it's a limit when x goes to 0 plus, the derivative of the top is 1 over x, that we know, and derivative of the bottom. So to find the derivative of the bottom, what we can do is we can rewrite this one like 1 over xp. You can rewrite this one as x to the negative p. And then we can use the power rule. So according to the power rules, the derivative is negative p x to the negative p negative 1. So that's what you get as the derivative for the of the bottom. So it is, so we can write it as a negative p x to the negative p negative 1. Now what we want to do is we want to see the algebra and simplify this one. So the best thing that we can do is try to get the denominator 1. And then actually before we do that, we can pull the negative 1 over p out of the expression, then it's going to make the algebra easy. So let's do that. And then what we can do now is, so let's see, we have 1 over x here, and in the bottom you have x to the negative p negative 1. So the best thing that we can do is to remove, to cancel the bottom term. So let's multiply by x to the p plus 1, the opposite sign. So x to the p plus 1. So right after we do that, you can see, so this term get cancelled out because it's going to cancel out and you get 1. So this become 1. That means the denominator is gone. So now so you simply get negative 1 over p limit x goes to 0 plus x to the p. That's what you get, x to the p, and when x goes to 0, x to the p goes to 0. That means the whole term goes to 0. So that's what you get as the limit for this problem. So it's a very interesting problem. So you can try now what happens if p is negative. So that's like a question for you. So thank you for watching. So let's meet in the Bernoulli rule type 3 in the next video.